Okay, so as you know, I've got this kidney stone, and so I'm not in great shape, but I think I can do the lecture anyway. But instead of writing on the board a lot the way I normally do, I will use the projector. So let me begin by saying just reviewing some elementary things. Chapter 2 is what I want to do today. But apart from doing Chapter 2, I want to jump back into Chapter 1 and say a little more about the singular value decomposition. And in Chapter 2, I want to emphasize the curl. I think the curl can be very confusing, but if you just look at it in the simplest way, then it's better. So this is stuff that I'm sure you know about. You know what a derivative is. You know the derivative of a monomial. You know what partial derivatives are. What I did introduce here, though, is I just show you or remind you of some of the many varieties of notation that exist for derivatives. F prime is a derivative typically for space. Double prime, of course, is a second derivative. Time derivatives are often indicated by dots, and double dots are second time derivatives. For higher derivatives, you can use parentheses, or you can use a notation like this, but it never ends. Well, it does end, but there are various other subscripts. For example, if you have a function of x and y, instead of writing d by dx or something else, you can just write f sub x. And as long as you have established the convention, then that's what you can use. So, in particular, in discussions of differential equations, it's often useful to use f sub x for the derivative of f with respect to x. And f sub x y is the triple derivative of f with respect to x and y squared. By the way, would you be better off without the overhead lights? What do you think? Yes, no?
Doesn't matter. Yeah. It's the same.
Sure. So this is a notation, as I said. Now, another notation that is used a great deal in special and general relativity is to take the variables x, and usually one considers 4 space-time variables. So you've got x1 to x4, or x0 to x3, and you label derivatives by commas. So comma k is the derivative with respect to xk. Comma kl is the derivative with respect to both xk and xl. So these are notations. It's just good to look at them a few times to make sure that you've noticed them. All right, the next topic is the gradient, and the key thing is the change dp, that's a vector, in a point p, that's a 3 vector, due to changes in its coordinates, the u's. And that, of course, is going to be that change of dp is going to be how the vector changes with respect to u1 times u1, how it changes with respect to u2 times u2, how it changes with respect to u3 times the change in u3. And then these derivatives, one writes as vectors e1, e2, e3. So that's a nice little expression like this. What you can typically do, of course, is you want these vectors to be orthogonal because it's nicer to have things that are orthogonal. And here they're not necessarily normalized. EI dot EK is HI, HK. Those are 2 scale factors times the Kronecker delta, delta ik. By the way, if anyone wants, has a question, wants food, ask a question, okay. So, in terms of these orthonormal vectors, so what you do is you take gosh, I think, yes, that's a derivative sign there. It doesn't look like one. But if you take the vector Ej and divide it by the scale factor Hj, then you get something that's normalized. And in terms of that, you can write things like this. So change in coordinates, scale factors, unit vectors, orthogonal unit vectors. And these orthogonal unit vectors in 3 dimensions have, of course, the standard cyclic cross products, where epsilon ijk is that totally antisymmetric Levi-Civita symbol. So in rectangular coordinates, the change dp is, of course, the changes in the rectangular coordinates, and the change in the vector is like that. And yeah, in rectangular coordinates, normally we use scale factors that are unity because there's no reason to make them more complicated. But in cylindrical coordinates, what you have is that the way that if you change the coordinates rho, phi, and z, then the coordinates change in a somewhat subtle way. The middle coordinate, or the position, changes in a somewhat subtle way, namely rho times the change in the angle. So it's the moment arm times the change in the angle times the unit vector. And in spherical coordinates, it's a little more complicated. R hat dr is normal, but theta hat d theta is down like that. It's r theta hat d theta, so the longer the r vector, the longer the movement. And r sine theta d theta is for phi. Actually, it's r sine theta d phi. Anyway, so the scale factors in the spherical coordinates are 1, r, and r sine theta. And so these are the coordinates, and these are the standard coordinates we use all the time. So the gradient of a scalar function is just defined so that its dot product with the change in the position vector gives you the change in the function. So df dot dp. This is worth remembering, by the way, because you can get confused as to what a gradient is if you haven't read a good definition lately. But the idea is that the gradient dotted into the displacement gives you the change in the function. The gradient of the function dotted into the change in the displacement gives you the change in the function. And so what you have is the gradient, the x component of the gradient times the unit vector in the x direction, and so forth, so on. So this is the gradient as a vector, and then this is the displacement as a vector with scale factors, coordinate changes, and unit vectors. And when you dot it all out, you get the one component of the gradient times the first scale factor times the change in coordinates, plus and so forth, so finally the third component of the gradient times the scale factor times the change in the third coordinate. And then you can rewrite it as df, or as partial f partial u1 plus partial f partial u2, and so forth. It's always of this form because f depends upon these coordinates. So you can always write the change in f as the partial derivatives times the change in the coordinates. And so the gradient on orthogonal coordinates then takes this form, which follows from all this. And in rectangular and spherical coordinates, these are particular orthogonal coordinates. This is what the gradient looks like. And now something I want to focus on a little bit is this little thing here. This is something you probably learned, you certainly learned in college. I mustn't breathe and drink at the same time. The gradient of 1 over r is minus r hat over r squared, or minus r vector over the length of r cubed. And similarly, if r is the distance between vector r and vector r prime, then the gradient of that is minus r prime over r minus r prime cubed. And the differentiation here is with respect to r, not r prime. So these are, of course, derivatives that you learned in electrostatics, and but they're going to come back to us in just a moment when we look at the divergence more carefully. Any questions? All right. So, I assigned new homework. I put it on the class webpage today. So it's some of the later chapters and later problems in chapter 2, chapter 1, and some of the problems in chapter 2. Okay, the divergence of a vector in an infinitesimal cube. So this is the divergence of a vector defined as a function of a point, at a particular point. And it's defined as the integral S of the vector V over the surface of the cube divided by its volume. So that's sort of a complicated phrase. It's the integral of the vector over the surface of the cube divided by its volume. And the volume, of course, is the scale factors times the changes in coordinates. These are orthogonal coordinates. And the surface integral then is a sum of 3 surface integrals, say, over the cubes. We're looking at a cube here. Cubes, 3 forward faces, and minus the sum of the 3 integrals over the 3 backward faces. And so what you've got is you've got that V1 and H2, H3 is the surface of the cube, surface area of the first face of the cube, the forward first face of the cube, times V1 is the integral of the vector, of the first component of the vector, and then you subtract out the integral over the back face of the cube. So that's why you have a derivative here. And so you have partial with respect to x1, dx2, du2, du3, and then du1, and so this is then what that is, and the divergence then is the ratio, so we divide by the volume being the product of the scale factors times the product of the differentials. So that means this goes away and this goes away, and what you have is simply these 3 terms. Does anybody want me to draw that more clearly on the board? In rectangular coordinates, it's very simple. You've seen it many times. It's actually, that's a mistake here. That should be dvx, dv sub x, dv sub y, dv sub z here. I left the subscripts off this thing. Let me see if I can just put more on this. All right. right, so the cylindrical coordinates, it's written this way, spherical coordinates that way, and all these three are applications of this formula 219. All right, now here's something I want to emphasize. Inasmuch as we've defined the divergence as the surface integral divided by the volume, if we take a large number of infinitesimal cubes and imagine that we're going to integrate a vector dotted into the area, that's something I should have mentioned earlier. It's not simply the integral over, but it's the vector dotted into the surface elements. And so here, if you have an infinite number of very tiny cubes, you can approximate any surface, and the sum of the products of the divergence in each cube times its volume is the sum of the surface areas over the cubes. On the other hand, all the surface integrals on the interior faces, so you imagine putting together, if you want to make some shape that, I don't know, looks like my cup, say, then you'd have a million different tiny pixels, but the surface areas that were inside the cup would cancel, because one would be facing outward and the other one facing inward. The face for this cube would cancel, the positive face from this cube would cancel the negative face from that cube. And, or approximately cancel it. Anyway, so what one is left with is simply the integral over the surface of the cube. And that is then the integral of the divergence throughout the cube. And that's this equation here, which is Stokes' theorem. This is used all the time in physics. So a vector dotted into its area is equal to the divergence of the vector integrated over the volume enclosed by the area. Now, here's something that you may not have heard a great deal about. It's something that was introduced by Dirac, the delta function. And I think mathematicians have tended to leave it out. Although Gelfand, actually, whom I mentioned last time, I think, not only does he write clearly, but he wrote 5 books really clearly about delta functions, but he generalized the concept and analyzed delta functions in a much broader context and in much more detail, suitable for mathematics as opposed to physics, but it was basically Dirac's idea. So let's consider this. Let's consider the function r hat over r squared and take its divergence and integrate over any sphere. So if we do that, we're going to use the previous formula. The previous formula said that the integral of the divergence over some tiny sphere is the surface integral of r hat over r squared dotted into the surface area of that tiny sphere. And no matter how small that is, notice what happens here. We've got an r squared in the denominator. So this becomes r hat over r squared. The area is r squared r hat d omega. R hat dot r hat is 1. R squared cancels r squared. All we have left is d omega. So we get 4 pi. So this is a remarkable result. It tells you that if you integrate the divergence of r hat over r squared, which is the thing that you get when you fool around with Gauss's law in electrodynamics and electrostatics, if you integrate the divergence of r hat over r squared over a volume, what you always get is 4 pi. And that's true no matter how small the volume is. Infinitesimal volume, you still get 4 pi. And so the idea here is that, more generally, the integral of the divergence of r minus r prime over r minus r prime cubed integrated over the volume, which by Stokes' theorem is r minus r prime over r minus r prime cubed, dotted into the area. And now when you work that out, you again get 4 pi. And these divergences then are examples of Dirac's delta function. And what the delta function is something such that, suppose you were integrating over some volume, an arbitrary volume, a function f of r, and you multiplied it by the divergence of r minus r prime. Well, this would give us 4 pi, but the integral would contribute only at r vector equal to r prime. And so the function f of r will be evaluated at f of r prime, not all over the volume, just at r prime. And the magnitude would be 4 pi times f of r prime. So this is how a delta function works. When mathematicians talk about it, they use nicer language. They say that a delta function is a continuous linear functional that maps functions onto numbers. And that's, if you think about that, you see that's a very nice expression. What this says is that this funny thing here, when integrated, takes this function f of r and moves it into 4 pi, maps it into 4 pi times the point f of r prime. Any questions? Anyway, it's important to understand delta functions in physics, and they have lots of uses, and in fact, when you study quantum mechanics, you start worrying about complete sets of wave functions. And it turns out a complete set of wave functions is a set of wave functions whose sum will give you a delta function. And you can see some nice graphs of that later in the book. Okay, Gauss's law. The divergence of the electric field is the charge density divided by the electric constant. So this is Gauss's law. This is, of course, very important. And let me call something to your attention here. Normally, in physics, we sort of start with Galileo and go forward and teach mechanics. Okay. Well, I think that's absurdly slow. And in fact, the slowness is I think damages students, because students get the impression that physics is mechanics plus some fancy new stuff. But in fact, the truth is that mechanics is the fancy new stuff. Mechanics was just kind of an illusion. So in particular, what you have here is that the divergence of the electric field is the charge density. That's what's called a constraint. And what's meant by that is that there are really no time derivatives over here. Certainly no second time derivatives. And in fact, E is the electric field. It could be totally static. The divergence of the electrostatic field, or the electric field, is the charge density divided by the electric constant. As I said, that's a constraint. Whereas in mechanics, you don't have constraints normally that the position is in a particular place, or the momentum is a particular place, or the momentum plus the position has some value, or there's something really special going on, like in this equation. And what's true is, what is this? This is characteristic of electrodynamics. And then, what are the other theories we know about? Well, gravity and general relativity, it's the same kind of thing. There were also constraints. And then, if you look at the weak interactions or the strong interactions, you also have theories like electrodynamics and general relativity. Non-abelian gauge theory is very similar, and those theories have constraints in them. So none of this is like mechanics. Mechanics, no constraints unless you do something artificial, like have the bottle rolling off the table. Something like that is a constrained problem. And in fact, those sorts of problems should be studied more in mechanics, because they're closer than anything else in mechanics to real physics. Okay, if we now take Stokes' theorem, we can integrate the divergence of the electric field. That'll be the surface integral of the electric field over the surface of something. This partial V means the surface of V. And del dot E will be rho over epsilon 0. So this will be the total charge over epsilon 0. So the total area of the electric field over a surface is the total amount of charge inside, which is a rather nice, simple, remarkable relation, which I imagine the first persons who figured it out must have been amazed for days. All right, let's go to Laplacian. Laplacian is simply defined as the gradient of the divergence of the gradient. So in orthogonal coordinates, you just use the formula for divergence, apply it to the gradient, and you get this structure here. In rectangular coordinates is very simple to look at. It's just the sum of the orthogonal squared derivatives. D by dx squared plus the square of d by dy. I'm sorry, it's the second derivative. It's the second derivative. It's the second derivative of f with respect to x plus the second derivative of f with respect to y plus the second derivative of f with respect to z. So it's a sum of second derivatives. In cylindrical coordinates, it looks like this. So what you do is you again put together the divergence and the gradient. And in spherical coordinates, it gets more complicated. And I wrote two different ways of doing this here, which I urge you to take a look at, because they're not quoted. Both, I forget which one is quoted all the time. The other one isn't quoted as often, and it's actually often much more useful. Because you see here, you just have one derivative to deal with. Here you have a derivative, you multiply, you have another derivative, and then you divide. Anyway, it depends. Sometimes this one is more useful, sometimes that one. But in fact, what you might do is check that this is the same as that. And if it isn't, send me an email, please. Yeah, also, just today I found a mistake in the book. If you find a mistake in the book, typo, whatever, or an error, send me an email. Okay? Please. Okay, more about delta functions. Delta function is Laplacian of 1 over r. Well, if you take the gradient of 1 over r with the representation we previously had of the delta function, we can write the delta function as Laplacian. So let's see, why don't I go back to so 2.26, just to remind you what this was. Okay, so there's, in the simplest case, the divergence of r hat over r squared. That's the delta. That's a delta function. And if we go here, we have the, well, r hat over r cubed was the gradient of 1 over r. So you combine the gradient with the divergence, you get the Laplacian, and you get this, you get this delta function. So minus Laplacian of 1 over r is 4 pi times the three-dimensional delta function. And similarly, minus the Laplacian of 1 over r minus r prime is 4 pi three-dimensional delta function, r minus r prime. And this, let's see, what should I say? We're differentiating with respect to r, not r prime. I was going to say something else, but I've forgotten. Any questions? Anyways, these delta functions are your friends. And in fact, I remember as a graduate student having these absurdly long, multiple Fourier transforms. But then Dirac would save me because one integral would give a delta function, that integral would correct, and that delta function would collapse another integral. So all of a sudden, 6 integrations went down to 0. There were typically still others left. Sometimes it was 8 integrations go down to 0. So delta functions are your friend. They're something to become friendly with. Questions? Electric field of a uniformly charged sphere. This is just an example. This chapter isn't so long, so I can do the examples. So the electric field is minus the gradient of the scalar potential minus the time derivative of the vector potential. So this is a vector. And if it's a static problem, then you don't need to worry about the time derivative of the vector potential. And in that case, you can take the divergence of E and you get minus Laplacian of the scalar potential. And then in spherical coordinates, if we have a uniformly charged sphere, so we don't have to worry about derivatives with respect to theta or phi, then our Laplacian of the field collapses in spherical coordinates to this very simple expression. And here, even better, we've got rho to be the uniform charge density. So what we do then is we multiply both sides by r, integrate twice, and we set a constant a be the derivative of phi, not the derivative, the value of phi at the origin. And we find the sphere to be, the potential to be a minus rho r squared over 6 epsilon 0. Outside the sphere, the charge density is 0, so the second derivative vanishes. And that's, again, Gauss's law. Integrating twice again, we get the potential outside the sphere as just B over R. So this equation was 1 over R d2 dr squared. R phi is 0 in that case. Multiplied by R, we still get 0. So the second derivative of R phi is 0, and the answer is that, well, use the equation. R phi double dot is 0, and you integrate twice, and you get just a 1 over R potential, which is, of course, what you expect as a Coulomb force for as you go away from a uniform charge, a symmetric charge, spherical symmetric charge. So you integrate twice, all right, I've done that already. So the electric field then is the negative gradient of the potential. So on the surface of the sphere, where the interior and exterior solutions meet, you match these boundary conditions. So you match the two conditions. B is an arbitrary constant for the exterior. R is, I guess, an arbitrary constant for the interior. And then you set B equal to rho R cubed over 3 epsilon 0. Anyway, you finish and you get our expression for the potential. It's a Coulomb field outside. Inside, it's a constant minus a quadratic term. Okay, so that's those topics. Now let me focus on the curl, because I think the curl is the most confusing thing of these. The gradient is simpler. Divergence is reasonably simple. The curl is kind of confusing, and so let me try to talk about it. So we've got two things going on. One is the directed area. Of course, in general, with area, you point your fingers in one direction, you then point them in the other direction. That's the cross product. Your thumb points in the new direction. So the cross product of two vectors is the area subtended by those two surfaces. That's just what we use all the time. Now, I want to do this material, and I think that I'll have to actually just get up and do this for you in the simplest terms, and rather than just talk about it abstractly. So what I'm going to look at is I'm going to have one, so the idea basically, let me just give you the thing that I'm leading up to. The thing I'm leading up to is that the line integral of a vector around the perimeter of an infinitesimal rectangle is the integral of the curl over the area of the rectangle. So that's really counterintuitive and surprising. And so let me show you, if you look at it in plain, simple terms, it's obvious, otherwise it's not. So this is a vector, it has components x, but now I'm taking this point as the origin, and I'm imagining this is my rectangle. Okay, this is the rectangle, and it has y component y, x component x. Thank you. Y component y, x component x. But what is the value of this x here? It's really, well, it's integrated over x, but I'm sort of going to ignore that because it goes from small x to big X, and I'm just going to average that. I'm not going to be fancy about that, so I'm just going to call that x. But where is it y-wise? It's down a certain distance. What would you like to call this distance? All right, let's call it d. Well, I'm going to call it epsilon. In physics, our standard small number is epsilon. So this thing is evaluated not at y, but at y minus epsilon. Up here, the component of the vector in the y direction is evaluated at x plus epsilon, this distance here, epsilon. X plus epsilon y. And again, y goes from tiny values to big values, so I'm just averaging that. Over here, we again have x, but now it's x, average over x, but y plus epsilon, because it's above the origin in the y direction. That's y. And then over here, it is y, and it's going to be x minus epsilon because it's displaced from the center of the square times y. Okay, now let's just look at what this amounts to. What is the line integral of the function f? The function f has components. I'm just doing 2 dimensions. You've seen 2 dimensions, you've seen them all. So it has x component, y component. So what is this? Well, we have a certain distance here. The distance is 2 epsilon. So it's 2 epsilon. Everything's going to be multiplied by 2 epsilon. And actually, everything's going to be multiplied by 2 epsilon squared. But maybe I shouldn't do that. Maybe I should just... Okay, what is the integral along here? Well, it's x of x, y minus epsilon, times, effectively, 2 epsilon, plus y of x plus epsilon y times 2 epsilon. But now, this one, you see you're going in the opposite direction to the vector. So you're going backwards. So you have minus x of x, y plus epsilon. And then you have minus y of x minus epsilon y. So this is what you've got. And so this is, and 2 epsilon is just because the length of this is 2 epsilon, the length of this is 2 epsilon, and so forth. Now what's this? This is minus the derivative of x, partial derivative of x with respect to y, times epsilon, because that's the difference, epsilon. This one is plus y, partial of y with respect to x times epsilon. This one is minus partial x, partial y times epsilon. And this one is minus partial y, partial x times epsilon. No, I hope I got those minus. I think I have too many minus signs. All right, let's get this straight. X here, the first x, y minus epsilon, so that's right. This one is x plus epsilon, that's right. This one is going backwards, but it's positive, so that's right. Ah, there are 2 minus signs here. So, what is this? This is, apart from a factor of 2 epsilon squared, this is what the curl, this is the z component of the curl. The z component of the curl is partial y, partial x, minus partial x, partial y, and in fact I've just got that twice, don't I? So what we really have over here is really 4. So it's 4 times this thing. And so this is 4 epsilon squared, what we call the curl of f. The curl of f, z component. So we're only component, we're working in 2 dimensions, so effectively we have the z component. And you may think that I'm doing this in a very, very careful way, and that it's kind of silly because I'm doing something that's very elementary. But what I'm doing here, it turns out that in non-abelian gauge theory, and to some extent in general relativity, although it's more subtle, one has to go through exactly the same argument. And the conclusion you come to then is that the integral of a vector around a perimeter is equal to the integral of the curl over the area. And in the case of non-abelian gauge theory, then it's that you have some vector, which you might write as a 4 vector with a Greek index. I don't really think we need to use Greek all the time. And then what you do is you then have an epsilon ijk, and then you'll have the jth derivative of ai. And it gets more complicated than that, though, because you have nonlinear terms. Anyway, so the integral of the gauge field around the loop is the integral of the curl of the gauge field over the area of the loop. All right, now let's see where I was here. So let me write it in yet another form. The integral, and we put a 0 there or an O because we're going all the way around. F dot dl, and these are both thought of as vectors. This is, well, the way I wrote it was partial Fj Hj partial ui minus partial ui, oops, hi, partial uj. And another way of writing it, which is sort of a version of one of Stokes' theorems, the integral of the curl of f over some surface is then the integral of f dot dl around the surface. Let me just see, I think I could have emphasized that more. Now, I mentioned many times, or at least more than once, the Levi-Civita symbol. This is something that is epsilon ijk. Ijk go from 1 to 3. And this is totally anti-symmetric. So epsilon 1, 2, 3 is 1, is minus epsilon 2, 1, 3, and so forth. So it's just totally anti-symmetric. This gives you a very nice way of writing curls, namely that the curl of a vector, you can think of it as a sum on ij and k of e hat k, the unit vector in the k direction, hi hj epsilon ijk partial of hj fj over ui. So that's the way it is in general orthogonal coordinates, but in rectangular coordinates it's much simpler than that. Let me see if I've got this. So in particular, in rectangular coordinates, you simply have, or if you label your coordinates 1, 2, and 3, then the curl of fi is epsilon ijk, the derivative with respect to xj, the k component of the field. And so then, what you're summing here is over j and k from 1 to 3. And for each I, you have a particular I there. So this is the quickest recipe for curls, and in rectangular coordinates, it's pretty simple. It can be confusing in cylindrical or spherical coordinates. I'm sorry. In general orthogonal coordinates, one writes it this way: the curl of f is then 1 over the 3 scale factors, and then a determinant of scale factor, unit vector, and then under here you have a partial with respect to the first variable, partial with respect to the second variable, partial with respect to the third variable, and then h1, f1, h2, f2, h3, f3. So this is what I meant up there by, somewhere there by summing over jk. So I give the formulas for the various cases, cylindrical, spherical, and so forth. Now, it turns out that one of the useful things about this formula is that if you combine it with another formula, with other formulas that are similar, you could use these Levi-Civita identities, which I'm actually assigning as a homework problem. So you sum I equals 1 to 3, epsilon ijk, epsilon imn. And now let me tell you how to remember this, if you want to remember it. It can be really useful if you remember it. You first say to yourself, okay, we're summing over the first index, and the second and third indices in both cases are free or general. So what the first thing you do is you write 4 Kronecker deltas. And then you put a minus sign in between them. Then what you do is you take, let me just make sure I get it right. So you take this one and that one and write it this way. And then you take this one and that one and write it this way. And then you swap them. So you have JN, KM. So that's how you can, if you want, that's how you can remember the identity. Of course, these days with Google, you don't need to remember anything. You just need to have fingers that work, or mouse that works, or screen that works. But back in the dark old days when I was young, these were much harder to come by. You didn't have Google. So as I said, these Levi-Civita identities, this is one of them. Let me give you the other one. It's the sum ij equals 1 to 3. Epsilon ijk, epsilon ijm. So now we're summing over 2 indices. So effectively you can wait a minute, ij, I didn't write this properly, ijn. And the answer here is 2 delta kn. So here, this is kind of obvious because suppose I and j are two different integers between 1 and 3. Then this is going to be 0 unless k is the other one. So if this is 1, this is 2, this has to be 3. If this is 2 and this is 3, this has to be 1, and so forth. And so you get then that, well, you wind up with this. That the only way it can work out is for k equal to n, and then it works out twice. So that's how it works. Now, the reason why I like these Levi-Civita identities is that when you're dealing with rectangular coordinates, as opposed to these general orthogonal coordinates, if you're dealing with rectangular coordinates, then the formulas for curl and divergence work really very smoothly. They're the simplest formulas in the chapter. And when you use these identities, you can make a lot of progress. And so, for example, suppose you do this. Suppose you ask for what is the curl of the vector potential. And if you just write it that way, that can be confusing. But if you say, well, I want the ith component of the curl of the vector potential. Well, let me just tell you what the answer is. The answer is that it is the gradient of the divergence of A. So that means the ith divergence minus the Laplacian of A and the ith component of that. And again, in terms of rectangular coordinates, this is all reasonably straightforward. This is this one here is di ai gives you the divergence of A if we're just in ordinary rectangular simple coordinates, and then you're going to take the derivative of this with respect to xi, so that's this term, and this term is the ith component of the Laplacian, so this is minus d2a di, let us see. Let me use this. So it's what I should have here is a k that we're summing over, and it's an ai. So that's what it looks like in rectangular coordinates. So in other words, this thing is the gradient of the divergence minus the ith component of the Laplacian of the ith component, I guess is the way to say it. Okay. So let's see. We've already done Stokes' theorem that the integral of the curl is the integral of f dot dl. Let me go to Maxwell's equation. among the nicest equations in physics. I'm talking about the empty space Maxwell's equations. So we have the divergence of E. What is the divergence of E? An empty space.
The charge. The charge density. The charge density.
What?
The charge density.
I'm sorry, my hearing isn't very good. What?
The charge density.
Huh?
Charge density.
Yes. What is that in empty space? What is the charge density in empty space?
Oh, 0. Yeah.
Yeah. Okay, so this is one of Maxwell's equations right here. Another equation is the difference between electricity and magnetism, namely that the divergence of the magnetic field has always been observed to be 0. Now, there was some interest maybe 40 years ago as to whether there might be magnetic monopoles, like electric monopoles, electric charges, whether there might be magnetic charges. But so far they haven't been found. Another of Maxwell's equations in empty space is that the curl of E is minus B dot and C squared, the curl of B, is E dot. So these are some nice Maxwell equations. Now, what these imply is that the voltage drop, let us say, if you integrate the electric field around a loop, this would be minus some time derivative of potential. Actually, looking at that, a little bit puzzling. But anyway, and this is equal to minus the integral B dot over the area. So this is the thing that you have noticed many times, namely that if you have a loop of wire, you have an oscillating magnetic field, this increasing and then decreasing magnetic field will produce a current going this way and then that way, or that way and then this way, depending on which way the signs work out. And this is then a consequence of the fact that the curl of E is minus B dot. This other equation tells us that B, which is the integral of B dot dx, say, is 1 over c squared, the time derivative of the electric potential, and that turns out to be 1 over c squared, an integral of E dot dA. So the integral of the time derivative of the electric field is equal to, actually, do I have this right, or do I screw this up? Let's see. The integral of the curl of B over the area is going to be the integral of the line integral of B see, I may have been a little bit sloppy here. In any event, these are certainly Maxwell's equations, and if you combine them, what you can do is you can use the curl identities, the Levi-Civita identities, and these work out very directly in ordinary rectangular coordinates. Then what you do is you find that the curl of the curl of E is the gradient of the divergence of E minus the Laplacian of E. And in empty space, the divergence vanishes, and so this is just minus Laplacian of E. And this is also equal to minus the curl of the time derivative of the magnetic field, which is minus the second derivative of the electric field over c squared. So what I think the way in which one goes to this thing is one takes this curl of E, and the curl of E is already B dot with a minus sign. And so one gets this equation, and then a similar thing for B, namely that the curl of B is the gradient of the divergence of B. Well, that vanishes, minus Laplacian of B, and one can then rewrite that as the curl of E dot over c squared, which is minus then B squared, B double dot, what am I saying? B double dot over c squared. And of course, these are the wave equations. In other words, Laplacian of B is minus B double dot over c squared. Laplacian of E with a minus sign is E double dot over c squared. And of course, this is how electromagnetic waves propagate. Well, we're just about out of time. Of course, notice the last sentence of this chapter, namely that the exponentials obey these wave equations and obey them very easily because you take the sum of the second derivatives of the exponential, say, you take e to the I k dot x minus omega t, and you differentiate with respect to each of the x's twice. You get k squared, you differentiate with respect to t squared, you get omega squared, and so you get minus k squared, k vector squared, minus omega squared. And what you do, though, is you have an extra minus sign there, and so this is 0. I'm leaving out c. I think we need a c here, but anyway. By the way, this is something that you might want to get used to at some point. These are what are called natural units. In natural units, you just assume that you measure, first of all, distance you measure in light seconds. So distance you convert it to time. And then you make similar transformations until you measure everything in terms of some mass and so forth. And that way one can get rid of all those constants so you don't make mistakes doing the constants. Of course, eventually you have to bring them back in. But only when you get to the final answer. And then it's easy to bring them in because you know that you've set, say, Planck's constant equal to 1, or rather h bar, Planck's constant divided by 2 pi, you set equal to 1. You set c equal to 1. And so when you finally get an answer for the mass of the electron or the length of some object, you just add gratuitously factors of h bar and c until the units work out. And since you set h bar and c equal to 1, you can add arbitrarily many of them. And so you just wait till the units work out. And the units of h bar, of course, are energy times time, and the units of the speed of light are distance divided by time. Okay, well, I hope this kidney stone comes out before class on Tuesday. I did get an appointment with the urologist on the 31st of January. This is American healthcare. So the medical schools only admit a tiny number of medical students each year. We have a shortage of doctors. Doctors are paid normally. In New Mexico, we can't afford to pay them, they all leave. So I get to be seen on the 31st of January. All right, might as well turn the thing on unless you have a question.